Here we go once again with some physics AS level. We're going for 2009 module 2. This is from the summer exam. What we're looking at today is question 7. It's all about quantum physics, lasers and energy levels and de Broglie wavelength. Let's get going then. Question 7. The term laser stands for light amplification by stimulated emission of radiation. Figure 7.1 illustrates the electron arrangement within the atom of a laser before it has been switched on. Most of the electrons are in their ground state, with an occasional electron in excited state. So here's your ground state level, here's excited state level, and there's just one of those electrons up at the excited state level. On figure 7.2, draw a possible electron arrangement when the laser is switched on. What physically happens within the laser whenever it's switched on is that the gas that's within it, the medium that these electrons exist in, helium, neon mix usually, they are pumped with maybe an electrical discharge or with photons of light, and this causes the electrons then to exist at a higher state, so higher energy state. So let's just circle these, draw these in, boom, there they all are. Now the reason why I maybe drew one or two of them down here is because not really all of them will be up at the excited state. Some of them will still be down, but whenever it's turned on, most of them are at the excited state rather than the ground state. Part number 2 then, what is the name given to this situation? Well, more of them are up at this level. Usually they are down at this level, so it's known as population inversion. Part B, spontaneous emission occurs when an electron randomly falls to the ground state. What causes electrons to fall due to stimulated emission? So spontaneous emission is whenever it's random, but stimulated is something that is caused to happen. This is the effect. So there's something that causes this, and this is the effect. What's required then is a photon that is equal in energy to the difference between the ground state and the excited state that the electron exists at. So a photon absorbed by this electron here, or by the atom that this electron's connected to, will then cause this electron to drop down. Because of the electron falling down, it then emits a photon of the energy difference. And that means 2 photons will then be travelling. So if you imagine the first one coming in, which is of the same energy as the difference between these two, hits the atom, this electron falls down, and then 2 photons go out together. Let's fill that in down at the bottom here then. Photon with equal energy to the energy level of the excited electron. Now, because it's a photon, we can also describe it in terms of its frequency or in terms of its wavelength. As long as the frequency or the wavelength is the same as the jump in energy level that the electron has made, then this would be correct. Let's move on then to the last part of question 7. It's part C. Laser eye surgery uses a computer-controlled excimer laser. One such laser has argon fluoride as the lasing material. It produces electromagnetic radiation of wavelength 193 nanometers. Calculate the energy of an electron's excited state if it relaxes to a state with an energy of minus 9.18 electrovolts and emits the radiation of wavelength 193 nanometers as a result. I'm going to use the diagram down here to help explain this a bit more and zoom in. So what we have is the electron has dropped down from an excited state to the ground state, and this ground state has an energy level of minus 9.18 electrovolts. And what the electron has done as it's dropped down is that it has emitted a wave of electromagnetic radiation of 193 nanometers wavelength. Now we are being asked to calculate the energy of its excited state. So where was the electron to begin with? Well, the electron was up here and it's now dropped down to here, and this is the energy level of it now, and this wavelength is the equivalent drop of energy in the form of this wave, electromagnetic wave. So let's work out what the energy of this electromagnetic wave is, and then compare it to this, so that then we can find what this state up here is going to be, what this energy level is going to be. Let's then put in what we know and what we're trying to find out. We know the amount of energy that it has now. We know the energy that it has released in form of a photon of light of wavelength 193 times 10 to the minus 9. And we're trying to find out, well, what was that energy level before it released this? Two equations we're going to use for this. First of all, the Planck's equation, where energy is equal to Planck's constant times the frequency, and then our wave equation. So we're going to find out what the frequency is and put it into this equation using our speed of light and our wavelength. I'm just going to label these as well. This is our first equation, this is our second equation for whenever we do some substitution. Let's put some numbers into equation 2. So our speed of electromagnetic radiation, speed of light, is equal to the frequency, and this is times the wavelength, so 193 times 10 to the minus 9. And that's going to equal, F is going to equal 1.55 times 10 to the 16 hertz. Let's then substitute this frequency into this equation with using Planck's constant, and that then equals the frequency we put it into this equation, that equals the Planck's constant times the frequency, which gives us 1.03 times 10 to the minus 18 joules. Okay, a very small amount of energy. So we're just gonna, last thing we're going to do is transfer this into electrovolts. So divide the energy in joules by the charge of one electron, and that equals, let me just write that, E equals 6.44 electrovolts. Now, we're not quite finished. Let's just look again at this diagram on our left, and if you remember, it said that this here wavelength is the equivalent then of 6.44 electrovolts. So if the difference between minus 9.18 electrovolts and our top level here is 6.44 electrovolts, then what is this top level? Minus 9.18 electrovolts plus the 6.44 electrovolts equals minus 2.74 electrovolts. That must be the energy level up there, minus 2.74. Let's now move on to question 8. The de Broglie formula is quoted in your data and formulae sheet as equation 8.1. Alright, here we have the three variables, and what does each of the terms represent? Basically have to learn this off. The wavelength, of course, Planck's constant, and then momentum. Part B then, figure 8.1 is a graph of 1 over p against the wavelength, lambda. So state the numerical value for the gradient of the graph in figure 8.1 and include its units. This is, of course, a straight line graph that goes through the origin. So the equation of this line would be y equals mx. We can put into this equation as well then what y is, which is 1 over p, and what x is, which is lambda. So let's put that in, 1 over p on this side and lambda over here. And the last thing is just to fill in, well, what is the gradient going to be? So we look up at the equation here. Alright, we have lambda on this side and p on the other, so we have to get h over to the other side and leave this as 1 over p. So that's what we're doing, we're dividing both sides by h to get 1 over p on this side, and that leaves us with lambda over h on the other side. Now if we're going to put that in there, lambda over h is the same as 1 over h times lambda. So our y-axis, our x-axis, and then our gradient. So we need to work out what the gradient then is as a value if it's 1 over Planck's constant. So gradient is equal to 1 over h Planck's constant, which is equal to 1 over the value for Planck's constant. There we have it, 1.51 times 10 to the 33. Let's then work out what would the unit then be of this. For Planck's constant is the joule second, so the unit for this is going to be 1 over the joule second. So that's simply joule to the minus 1, s to the minus 1. The very last part of the question then, it says to calculate the de Broglie wavelength of an electron moving at 90% the speed of light in a vacuum. So we're being asked to calculate the de Broglie wavelength. We've been told its speed, we know its mass as well. We also have the value for Planck's constant, 6.63 times 10 to the minus 34, and then the relationship that brings that all together, where the wavelength equals Planck's constant divided by the momentum. The momentum is the mass times velocity. So Planck's constant divided by the mass times the velocity is equal to 2.70 times 10 to the minus 12. So that's what the wavelength is going to be in meters. And the last we look then at our solutions. Go, and here's our answers. Tick.